everyone! Today we are going on a pretty wild journey, all the way from the super hot center of our planet right up to the soil beneath our feet. We're going to explore the massive forces that are constantly shaping our world. Things like shifting continents and erupting volcanoes. So let's just dive right in.
Okay, so just for a second, think about the ground you're on right now. Feels pretty solid, doesn't it? But what if I told you that it's actually just a super thin, brittle shell on a dynamic, churning planet? And what if that shell is actually broken up into giant pieces that are always moving? Well, that's exactly the story we're going to unpack here.
All right, first up, our planet's inner layers. See, to really understand what's happening on the surface, we've got to take a trip deep inside. We're going to start right at the heart of the Earth and work our way back out, layer by layer. So the part we live on, the crust, it's really just a sliver. The real giant here, the layer just beneath us, is the mantle. And it is huge. I mean, it makes up a staggering 82% of Earth's total volume. You can think of it as the planet's massive engine room.
So right at the center of it all, we have the core. And it's actually a two-part deal. There's a solid inner core made of iron and nickel, and that's surrounded by a swirling liquid outer core. This is Earth's heat engine. The incredible temperatures down here are what powers everything else we're going to talk about.
All right, coming out from the core, we're back in that huge layer we just talked about, the mantle. It's made of hot, dense rock, rich in iron and magnesium. Now here's a mind-bending idea for you. Even though it's solid rock, over millions of years, it actually flows. Think of it like incredibly thick, hot tar. This slow, churning movement is called convection, and it's driven by that heat from the core. This is the engine, the force that drives everything that happens on the surface. It's a huge deal. And finally, we make it to the surface. This is our home, the crust. It is the thinnest, most brittle outer shell. A good way to think about it is like the skin of an apple. It's that thin in comparison. Now, there are two types of crust. There's the dense oceanic crust under the oceans, and then there's the thicker but less dense continental crust that makes up our land. All right, so we have our layers, but this is where it gets really interesting. That crust isn't one solid shell. Nope, it's broken into giant pieces, and they're moving. Let's take a look at how. This whole idea has a name, and it's one of the most important concepts in geology, plate tectonics. So the theory goes like this. The Earth's rigid outer shell, which is the crust and the very top solid part of the mantle, is broken up into these massive plates. We call that rigid shell the lithosphere, and these huge plates are kind of floating on a hotter, softer layer of the mantle underneath, called the asthenosphere. They're just gliding along super slowly over this gooey layer. So because these plates are always moving, they have to interact with each other at the edges, right? And this happens in three basic ways. One, they can collide. We call that a convergent boundary, and it can create massive mountain ranges like the Himalayas. Two, they can pull apart. At a divergent boundary, magma rises up from below and creates new crust. And three, they can slide sideways past each other. That's a transform boundary, like the San Andreas Fault, and that's where you can get some serious tension building up. Now, as you can imagine, all this colliding and pulling apart of gigantic plates isn't exactly a quiet process. Up here on the surface, it unleashes some of the most powerful events our planet can produce: volcanoes and earthquakes. All right, let's start with volcanoes. That classic picture-perfect cone shape that you probably imagine, that's what we call a composite volcano. Think of Mount Fuji. They're built up from many layers of sticky lava and ash, which is why they get so steep. Then we have shield volcanoes. These are pretty much the opposite. Their lava is much more fluid, really runny, so instead of piling up, it just spreads out in these thin layers. That's how you get these broad, gently sloping domes, kind of like a shield lying on the ground. The islands of Hawaii are a classic example. There are also cinder cones. These are often simpler. They're formed from explosive eruptions that basically blast small fragments of lava called cinders into the air. All those fragments just pile up around the volcano's vent, and boom, you get a steep little cone. And one more type, lava domes. You get these when the lava is so thick and sticky, so viscous, that it can't really flow, so it just piles up right over the vent, forming a big, steep mound. They're pretty cool, and you often see them forming on or near larger volcanoes. Now, what about earthquakes? Well, they happen when that built-up strain along a plate boundary suddenly snaps and releases. We measure them on the Richter scale. And here is the key thing to remember.
The scale is logarithmic. That means for each whole number you go up, the earthquake releases about 32 times more energy. So a magnitude 6 quake isn't just a little bit worse than a 5, it is 32 times more powerful in terms of energy released. That's a massive difference.
Okay, all this action, the melting, the pressure, the eruptions, it's all constantly creating and transforming the very material of the crust itself, which is rock. And this brings us to one of nature's most amazing systems, the never-ending rock cycle. This is the rock cycle, and it's a fantastic way to understand how the three main rock types are connected. Okay, so let's start with magma, molten rock. When that cools and solidifies, it forms igneous rock. Now that rock gets broken down by weather and erosion into little bits called sediments. When those sediments get squashed and cemented together, they become sedimentary rock. And then, if you take either of those rocks and cook them with intense heat and pressure deep inside the earth, they transform into metamorphic rock. And guess what? If things get hot enough, that rock can melt back into magma, and the whole cycle just keeps on going. All right, we've gone from the core to the crust. We've seen how rocks are formed. But there is one last, absolutely vital part of the story. How do we get from hard, solid rock to the soil that life itself depends on? You see, good, healthy soil is so much more than just dirt. It's a really complex mixture. About half of it is what you'd expect. Inorganic material, basically tiny bits of weathered rock. But the other half is a mix of water, air, and the really special ingredient, organic matter, which comes from living and decaying things. So the process starts with the parent rock, which gets broken down by weathering. That can be physical, think of ice splitting a rock, or it can be chemical, like rain dissolving it over time. But then living organisms jump in. They add that organic matter we talked about, and they are crucial for recycling nutrients. It's this combination of weathered rock and life that creates the fertile soil we all need. Okay, we have covered a lot of ground, literally from the core to the crust. So let's do a quick recap of the key concepts you'll want to take away from this. First, Earth's structure. Remember the three main layers, core, mantle, and crust. The key engine is convection in the mantle. That's what drives plate movement. And those plates can interact in three ways. They converge or collide, they diverge or pull apart, or they transform, which means they slide past one another. Second, remember the rock cycle. It's that beautiful system connecting igneous, sedimentary, and metamorphic rocks, showing how they're all constantly being transformed. And finally, soil. It's not just broken rock, it's a living system created from weathered rock plus that critical organic matter. So, the biggest idea to leave you with is this. Our planet isn't static. It's a dynamic, constantly changing and recycling system. The very ground beneath us is on a journey that's been going for billions of years and is happening as we speak. Which leads to a really fascinating final thought. Knowing what we know about these forces, where will the continents we know today end up in the next 200 million years?